All right, good morning, everyone. Thanks for joining us for our first tutorial series. There's a NSF program called ASPEN-Net. It's a project to build a quantum network here in the US. And as a part of this, we're launching this tutorial series to try to help build a larger community. And one of the things that we're aiming for with these tutorials is to first start off today's talk, the introductory talk will be about quantum networks, and then build up about kind of our approach to quantum networking as we go along. And so that'll be the first few months of this ongoing tutorial series. And then we hope to eventually broaden it to include more topics from more people from not just in the US, but potentially around the world. And so our first talk today is by Dr. Brian Smith, who's a physics professor at the University of Oregon, and he'll be speaking about quantum networks and applications. Now, Brian, he leads the Optical Quantum Technologies Research Group in Oregon, and he's really an expert in both quantum optics, nonlinear optics, and experimental quantum physics. He's done a lot of work on not just fundamentally trying to figure out how to use different, I'd say, properties of light, like the spectrum or temporal modes, and I guess now path, to try to build these larger entangled states or quantum systems. But he's also really focused on a lot of applications too of how we can actually use these quantum technologies to do, new and novel things. And so I first met Brian, I think in the mid 2000s when I was just a young graduate student visiting Oxford on an academic visit. And he was, I believe, a postdoc there, or a senior postdoc there. And he left an impression, very positive impression. And so it's a pleasure today to work with him and have him be the kind of lead PI on ASPEN-Net. So I'm going to turn it over to Brian. Thank you.
Well, thank you, Chris, there. So that's right. So I'm Brian Smith, part of the NQVL. So this is the National Quantum Virtual Lab here within the United States. And we are running a pilot project called the Attosecond Synchronized Photonic Entanglement Network. And here are the players who are part of this network, both university and government labs, and also some industrial partners involved in ASPEN-Net. So I'm going to tell you today, my talk is, if I can get the PowerPoint slides to go there. Quantum networks and applications. I will emphasize an introductory talk. So in this series, we are going to be having talks at different levels. This is sort of level -1. So this is a very introductory talk to give you my view, and it's only mine, of what you might call quantum networks and how you might divide them up. And so late last night, I asked ChatGPT to render me an image. I said, make a picture of a quantum network. And so this is what I got. And the text that came along with it was, here's a visualization of a futuristic quantum network showcasing interconnected glowing nodes linked by entangled photon streams. So take that as you will, but we'll be talking, it's not far off. I don't know about the adjectives describing the network, but hey, it's close. So I don't normally start with an outline, but I figured today would be good. Here's our little roadmap. We're going to start with some motivation in quantum information science and technology to motivate our journey. Then talk about classical information and classical networks. To preface then what quantum information is, that is how we encode information in quantum systems, and talk about entanglement, which is a resource which has no classical analog. So quantum entanglement is a resource for quantum information science. And then we'll talk about the extension to quantum networks, give a definition of what I mean by a quantum network, talk about specific applications of the networks and different approaches, and end with our approach in ASPEN-Net. Okay. So quantum information science and technology has these sort of three pillars. So I want to thank Mike Raymer for having a similar slide in one of his talks in the past that has promising new functionality for old problems and also new technology that might not even be available in the classical domain. So we have quantum computing, quantum sensing, and quantum networks, some call quantum communications, as the three pillars of quantum information science. So there are various things one might want to do with quantum computing, some optimization problems that you could solve, figure out how to design certain molecules for drugs, solar cells, light emitters, materials designs, pattern recognition, so traffic flow and routing. Again, that's related to optimization. Artificial intelligence, there's a lot of thinking about whether or not quantum AI is a different beast than the current AI, and decryption. And so this was ChatGPT's quantum computer. Then for sensing, we also have different things that we can sense, so different fields, biomedical imaging, GPS, distributed sensing. So these are just a handful of possible quantum sensors. And if you link up sensors, that's what we mean by distributed sensing, and that's why it's going to fall in also the quantum network. And again, ChatGPT's rendering of a quantum sensor. You can see there's a color theme going on with anything quantum, I guess. And finally, the quantum networks. So this enables some secure data encryption, remote quantum computing, distributed quantum computing, and these are key aspects and motivators for some work here, but also distributed sensing. And I think later in the series we'll touch a lot deeper and take a deep dive into one approach to distributed sensing. And finally, you can also realize multi-particle entanglement protocols, such as secure voting. So these are important motivators for pursuing quantum information science and technology. So, as I said, this is a tutorial. So here's my approach to classical information. You always have to introduce Claude Shannon, who introduced information theory in 1948. So my approach to teaching classical information as a physicist is that information is related to uncertainty about something. And the more certain you are about an event, the more information that you have, or the more information that you need in order to resolve some uncertainty. So an example, or rather making this more concrete, is that uncertainty is related to probability to predict an outcome for an event. Right? So an event is something where you perform an experiment and you see what happens, right? And you have to make some predictions about that, and the probability of different measurement outcomes or different outcomes of the experiment are related to your uncertainty about those outcomes. And complete certainty, so if you know exactly what's going to happen, then you gain no information by running an experiment. So, why do it? And a simple example that I've used in the past, so if you were one of my students at Oxford, you will recognize this slide. I used this in an intro quantum mechanics class once. So it's what I call the ball under a cup, right? So this is magic. How much information do we get by looking under one cup? So if we ask a yes/no binary outcome question, is the ball under the red cup? We find yes or no. So let's say under the red cup here, well, it turns out, nope, it's not under there, right? So this is defined as 1 bit of information. I've gained 1 bit by looking under the red cup. I need to ask at most m of these binary outcome questions, right? So where m is the number of cups that I have here in different colors. And I need to ask at most this. So what's the minimum number of binary outcome questions that I have to ask to determine where the ball is? And so a better, oops, I think I skipped. There we go. A better strategy is to ask different binary outcome questions. Is the ball on the left or the right-hand side, for example? And here we'll say, is it on the left? And the person would say, no. Okay, great. I've gained one bit of information, right? And then I could ask, okay, I could take the same strategy. Is it on the left-hand side of the remaining possible cups, the M over 2 cups, and keep doing that on, and repeat until there's only one cup left. And after, say, n questions, we'll have M over 2 to the n cups. So every time you're cutting out half of what's remaining. And the minimum number of questions needed to locate the ball occurs when M over 2 to the n is equal to 1. And you can solve that. It's just n, the number of n is equal to log 2 of m. And this is the amount of information that we get. Now, Shannon, I could also ask, it's not advancing. How much information do we get when asking an M outcome question? So I could just ask, under which cup does the ball exist? And if I ask that kind of a question, right? Okay, well, it's under this purple cup here. The amount of information that is encoded in that M outcome question is the same as if I did this minimum number of binary outcome questions, but now it's a different number of outcomes, right? And so this is the same information content for an M outcome question versus a binary outcome question. And so depending upon what kinds of measurements you make or how you encode information, you have to think through carefully how we quantify the information. And in general, what Shannon taught us was that each question we ask about a system is equivalent to a measurement, and the amount of information that we can gain from such measurements can be recast into the probability for a measurement outcome. So the information in these measurements is given by this sum, the negative of this sum of pj log base 2 of pj. When here pj is the probability to find, in this case, the ball under a cup. So this is a probability for measurement outcome J, and you're summing over all possible measurements outcomes that you could have. And in the previous example, the PJs were equal to 1 over M. So the probability of finding it under one of the cups is going to be 1 over M. So it's a flat distribution. But if you have different probability distributions, this generalizes this. And the power of this formalism is we can think about breaking down an image, an audio recording, a video, whatever, into binary number strings, bit strings, and transmit these through wires or optical fibers and reconstruct an image at the other end, or the recording, whatever. And that's how we're communicating today. And so Shannon's seminal work underpins all of the information technology that we have today. So one of the next key points is going from this concept of what is information to how do we encode information into a physical system. I thought hard about putting in Landauer's information is physical here, but I decided to leave that out and instead just take for those who've done any kind of electronics class, you should know what TTL logic is, transistor logic. Right, and this is how information is encoded in many, many different devices that we have today. So we have a logical 0 state and a logical 1 state. So we'll call the low state and the high state. And so in transistors, it's a voltage that sets the logical value of the bit. And so a logical 0, will, on the input of a transistor system, range from 0 volts to 8.8 volts. And a 1 state will go between 2 and 5 volts. And there's this gray region, well, white region in the middle where it's neither. So if you have a voltage there, there's an error. And on the output, you have a different level of tolerance that's accepted for the logical 0 and 1 states. And this is all done by basically agreement, right, across the boards of how we're going to have a set of standards for encoding information in transistor systems so that when you link them together, they should work fine. As long as they fill these specs, then you put two different devices together to make them talk to one another, they should work. Right? And that's part of the engineering, and that's something that we're going to have to do as we build up the quantum information network in quantum technologies. So just to keep in mind, the state here, high state and low state, these are referring to states of a physical system. Okay. So another approach to encoding classical information in physical systems is related to the electromagnetic field. Right. So we have the electromagnetic field. Forget that it's an operator. That doesn't matter. As a function of some phase. So think of this as the frequency times time, omega t, of the field oscillating. Right. And it's some amplitude, overall amplitude, times what we call the Q quadrature and the P quadrature that oscillate as cosine or sine. Right. And so here, what we have are a series of three different quadratures, three different electromagnetic fields for different average photon numbers. So going from n equals 4 to n equals 400. And what you see, this is a nice little Mathematica code that I wrote that gives you noise, right? And so for a very weak field, this is a classical, what we call a coherent state field. For a very weak laser field, right, there's this noise, and that noise is unavoidable. It's what we call the vacuum noise. So we can represent this field, this oscillating field, as a phasor in phase space, right? And so we have the Q and the P, and there's some angle over here that determines if there's some phase offsets in this argument of the sine and cosine. And there's some amplitude alpha here, which is related to this E out in front. And now in hindsight, I should have made this a mod alpha. And that is related to the average photon number, right? And so that's the distance away. Now, this little blob, as you bring it down to zero amplitude, right, as alpha gets smaller and smaller, you end up at what we call the vacuum state. And that blob stays the same size. So that is vacuum noise, and you can measure that. And so the idea is that as you go further and further away in larger and larger amplitudes, that vacuum noise becomes more and more insignificant, and you don't even see it when you have very bright fields. And so how do we encode information in this amplitude and phase of the field? This comes along with the name of APSK or QPSK or blah, blah. So amplitude and phase shift keying. And this is actually how a lot of data is transmitted. It's coherent information encoding in the electromagnetic field. And I think I remember visiting Bell Labs in about 2009 and learning that that's really how they did this. And that was the best technology at the time. It was interesting. I was like, wow, really? That's it. Okay, cool. Now, implementation of this is a lot harder. And so here we have a grid of 4x4. So this is a constellation. You'll hear, engineers talk about constellation diagrams in telecommunications. They changed the labels to Q and I. Okay. And they can encode now not just bits, but DITs, right? So D-level systems. Here, there's a 16-level system, and these represent different binary digits, right? So there's the 0, there's the 1. I tried to figure this out. So 0, 1, where the heck is 2? Down here. And there's 3, and then it bounces all over. Up here, 4. So you get the point, right? So you bounce around in which one of these amplitude and phase positions in quadrature space. We call this the quadrature space. Whichever one you fall in is your bit string here. This is your symbol that tells you the logical value that you're encoding into that physical system. So this is a multi-level system now. Okay, so that's information in physical systems. Now we're going to move to classical networks and various examples. Well, first of all, let's start with this little diagram here coming from this website that I snagged, where we have nodes and links, right? And each node represents some source of information, perhaps, and then the link is transmission. It's a transmittance link where information can flow. But more generally, these could be other things. So they could be social networks. These could be people, and these could be relationships. They could be telephone networks, right? So these could be locations, physical locations linked by a communications channel. They could be part of the power grid. There could be transportation networks, citation networks. But the point is that each node represents some kind of information source, and these could be some kind of relationship between these nodes. And the big one that we're going to focus on, and the one that's depicted in the image on the right, is the internet, right? And so this is a map of the internet that was done in about 1999, and this came from Bell Labs. And this was a graphical representation of the internet and the connectedness. So you can note that there are several different features about how dense this is and how specific nodes, like this one here, are connected to a lot of things. So connectivity is one of the important features there. Important properties of the internet that we're going to want to think about for a quantum internet. Well, the internet classically is globally accessible, so it can be accessed by anyone with a connection. It has a decentralized structure, so there's no single point of control. And that's important because if something goes down, say in Oregon, we don't want that to ruin the rest of your day, right? There's interoperability through standardization, right? So this allows a lot of different things, like you can connect with your mobile device. You can connect with your computer and other things, right? So having a set of standards allows you to access the internet and connect through using many different approaches. Flexibility to support various media types, text, audio, etc. The affordability, well, yeah, we'll have to work on that one. Scalability to accommodate growing user bases, ease of use, user-friendly interfaces for accessing information and services from this thing. So, these are things we should be thinking about for a quantum internet at some point, as it unrolls. And of course, these things didn't happen overnight, right? These weren't at the very beginning of ARPANET. It didn't look like this. And one key point about the quantum or the classical internet is that it is based upon what is called packet switching. So you take the information you want to send and you break it into small packets that can be independently sent across a network. They can route around in different directions. They can take different paths. And that has a lot of power in that it ensures efficient transmission. So you can have some redundancy as well. And that might be a challenge for the quantum internet. We'll have to think hard about that. And it's dynamic. So it's continually evolving and integrating new technology and applications. Ooh, right. So,
Brian,
yeah.
there's a question in the chat, and folks, if you have questions, feel free to, unmute yourself anytime and ask. It's a small enough group. I think we can do this. But the question is from Barbara, and it says, if there's only a quantum advantage in very selected tasks, why would one want to construct a complete quantum internet? Why not hybrid?
So I haven't gotten to what the plan is for the quantum internet. And so, yeah, I completely agree that at the beginning, there may not be, that's a very good point. So, yeah, I would just say that right now, we don't know what the best approach is going to be if we need an all-to-all connectedness, right? I don't think that is probably going to be the case. And if you want to call it hybrid, but I think there will be something like that. I do think it's important, though, to have access uh, through quantum channels rather than just classical channels. So right now, how you connect up to a quantum computer is through the classical internet. You cannot transmit quantum information. And so there are certain protocols that one might like to do on a quantum computer that you cannot simply access unless you have physical access to the quantum computer itself. So things like blind quantum computing, you cannot do at this point in time. And so I would say, yes, I think there's going to be a balance, right? Not everyone's going to have a quantum computer at their home, and but there might be, particular physical user interfaces where you could, uh, take your quantum bits and try to send those to, something. Hope that answers the question. Okay, and so so that was my classical view. Good on time. Now let's move on to quantum information. And so in quantum information, the fundamental unit of information is the quantum bit or the qubit. And so this is the state of any two-level quantum system. So this could be two energy levels in an electron within an atom. Two energy levels of an electron within what's called a quantum dot. This is a semiconductor system. Two energy levels in a superconducting system. So this is a superconducting circuit, for example, and potentially two polarizations of a single photon or two spins of an electron. So here we've got depictions of spin up and spin down, representing our zeros and ones. And we're going to use this little Dirac notation to represent our zeros and ones. So these are our logical states of our physical systems. And the n=1 ground state of hydrogen could be our 0, and the n=2 state could be a 1, for example. Now, similarly to classical systems, we can have D-level systems as well, so what we call QDITs. And these are the M outcome questions that I mentioned before. Rather than asking binary outcome questions, I could ask an M outcome question, and that would correspond to a physical system with D potential levels. So we could just count up 1, 2, 3, 4, 5, 6, the first 6 energy levels of hydrogen, and that would be a 6-level system, a 6 outcome question. What energy level does the atom occupy at the moment? And if you can coherently manipulate that, then you have this nice D-level system, and you can do quantum information processing and transmission with that. And yeah, most people don't utilize that kind of thing. Another example of that would be the arrival time for D different time bins for a photon, for example. So a key property of qubits is they can be prepared in any superposition state, right? Which has no classical analogy, right? So we could have the state of our system is no longer, well, it's on. The voltage is 1 voltage, or the voltage is, between one range or another. But I could also prepare my atom in a superposition of the ground state and the first excited state with different amplitudes. And these amplitudes are related to probabilities to observe the electron in the atom in that particular level. And the sum of the squares, so the sum of these probabilities has to add to 1. And for the experts, the information content is related to the von Neumann entropy, right? And this is just a generalization of Shannon's information content, this trace of minus the trace of rho log rho. So for the experts in the field here. Now, this little spiel on this image on the right came from IBM. This is their thought about qubits and their advantages. So I just wanted to point this out that, again, superconducting systems is the platform that they're pursuing, hence it's on the top. Trapped ions. So this is, again, IBM is focused on quantum computing. So trapped ions, we have some good friends here at Oregon that do trapped ions for clocks, for example. Then they have different properties, right? Different. I won't comment on which is going to be the better pony, but let's just say these are the players where you're working on computing. So there's superconducting computers, trapped ion computers. There are things based on quantum dots. These might be more for memories, but there's potential for quantum dots or um, other things like that that could scale well because you can fabricate things in a scalable fashion. Um, Photons, so there are a couple of approaches to doing quantum computation through photons. And then there are also neutral atoms. So these are definitely platforms for quantum computing that have a lot of emphasis and actually investment these days. And the idea would be that, okay, a quantum network would like to connect up many of these different things, these quantum computers based on these platforms. All right, so back to encoding information in photons. Um, so I touched upon this already a little bit. So we in the quantum optics domain tend to work on either two extremes of the quantum state spectrum. So if we want to talk about the state of the electromagnetic field, we could say fix the number of photons to 1 and look at what modes the photon occupies. So there are different kinds of modes that the electromagnetic field can have. So in an optical fiber, you can have these spatial modes, right? So these are the modes that you would look at if you're looking down the fiber. And sometimes if the fiber is single mode, it only has this TEM00 mode. But if the fiber is a bit bigger, it allows more modes. You could have these modes with little nodes in the middle. And the idea is that the bigger the fiber, the more of these spatial modes you can put in. And similarly, you could have different frequencies propagating along, or you could have pulses of light that have many frequencies, but they arrive now at different times. You can also encode in the polarization. So these frequency and time modes and the spatial modes, those represent multi-level systems, qubits, potentially. Or you could just focus on 2, right? So you could say 2 of these are my 0 and 1, like we do in an atom. And then the polarization is really fixed. And so polarization is a qubit. And we can encode information in 1 photon at a time using these type of mode encodings. Now, if we fix the number of modes, say 1, so you pick 1 spatial mode, 1 polarization, and 1 frequency mode, time mode, then the quantum state is back to this idea of what's the phase space distribution. So what are the, what's the photon number distribution? And, what are the phases between those photon numbers? Or what is the quadrature distribution, right? So what does this distribution look like in this quadrature space? So this side is the most common approach in quantum networks and probably what most people are familiar with, where we would say, okay, now I want to distribute a pair of entangled photons, right? And so let's talk about entanglement, right? And that's going to be our fundamental thing that we want to distribute. So entanglement is a topic of contention in some ways, but let's just come with a simple definition that it's the inseparability of the wave function of a composite system. So an example, 2 photons, A and B, prepared in this superposition state. So HV for subsystem A and B plus VH, right? So subsystem A is in H on this one here, and subsystem B is in the V state, has the V polarization, and vice versa on this side. So a measurement of photon A resulting in H implies that a measurement on photon B will give with certainty V. Right, so if I measure H, I know exactly that I'm going to have V in my B photon. And many wrongly interpret this as causing the state of B to change, and it doesn't, right? So, yeah, we could have an entire discussion about this, a very long discussion. And so the important point, though, is these measurement correlations. So if I measured the state A and got a measurement outcome V, then I'd know that if system B measured the polarization, they should see H. Now the point is, you can be system A and B could be far apart, and if you measure over here, right, system A, system B doesn't know your measurement outcome. It takes a finite amount of time for that information to propagate. And if they're far apart, system B has no idea what system A did. And the only way you can see these correlations is by sending classical information back and forth. And that's one of the key points that a lot of people forget. But the important point about entanglement is that these measurement correlations will persist in every matched measurement basis. So if you measure now in rotated bases, so diagonal and anti-diagonal, for example, you will still see the correlations, or in this case, anti-correlations persist. So, and that's all I'm going to say about entanglement. Don't want to call it spooky action or anything like that. So a quantum network, here's a definition, and this is not from this group here at NTT. This is my this is my definition, or one of my definitions. So a quantum network will consist of a set of nodes connected by communications links. So these nodes here, these are our communications links, so optical fiber or free space, and these are quantum information processing nodes, right? So these could be sources of photons, for example. They could also be detection units where you detect and process the classical information from the detection events. It could be memories, right? So they could be a quantum computer, a quantum memory, a quantum sensor, whatever. So all of these things fall under the quantum processing units. And quantum information can be sent along these channels by sending, for example, a single qubit, right? So I could send a single photon along here and then try to load an atomic system over here. And the single photon could have emitted from another atom on this node. But the point of a quantum network is to distribute entanglement between, say, a specified set of nodes, right? So here we've got A and B highlighted, and maybe we want to have A and B entangled between one another. And there are different routes we could try to get entanglement between there. And so part of what people are studying is what are the best ways, what's the topology, what's the layout of the network, the connectedness that will optimize, performing this, and also what are the routing, how do you schedule? That's all an open question, right? And this is part of the open research. But the point is we want to distribute entanglements across the network, and it doesn't have to just be end to end, right? Or point to point. This could be more than two nodes. So maybe we want to connect up multiple nodes within the network. And that is one of the services that a quantum network will eventually deliver. So we talked about what are the applications. I want to highlight this from the Center for Quantum Networks, CQN. Here's the website. They did an applications roadmap with a group of industry partners about 3 years ago, and I guess we're supposed to have a new version of this coming out in the next year. And the idea is that these have been identified as applications of quantum networks, some of the key applications. So we have things that we talked about on the first slide. But the interesting part about this is that we are also looking at the different resources that are necessary for a quantum network. So we have fidelity, synchronization, rates, qubit volume, distance, number of nodes, size, and weight. Right? And for different applications, you might need more or less of these different parameters. So these are 1 through 4 for the quantum resource. So qubit direct transmission, Bell state entanglement, 2-mode squeeze vacuum state, multipartite entanglement. So those are the levels of increasing challenge as you go further out. And so you can see there are different applications that require small size, weight, and power. So enhanced navigation, we want something small, for example. Distributed quantum computing, well, you need a lot of good fidelity rates, distance, nodes, right? But size, weight, and power is maybe not as important. And so this, I want to just throw out there as a useful resource for people to think about. And now the longer term vision. So this came from the DOE reports on quantum information science and applications roadmap from December of 2024. Thanks, Paul. It wasn't mine. So this is from the DOE report, and I thank Joe Lukens for pointing this one out to me. And so here, we have long baseline quantum telescopes as one application of a quantum network. Entangled synchronized clocks. I like how that's a halo here. Oh, and I guess this clock is also entangled over here. And distributed quantum computing as the sort of key applications here. And these, you can see, are what the key components or elements of the quantum network should have. So quantum repeaters, quantum routers, quantum switches, quantum transduction, quantum computers, quantum sensors, and entanglement sources. Right. So we have an entanglement source here in the middle that emits a pair of photons that are entangled. Part of it goes to a repeater here, which is going to perform a Bell state measurement. We'll talk about that here in a moment. And then the other photon goes off to this quantum switch, which can direct the photon into an appropriate quantum computer. We have a router over here that can route this other photon from the repeater around to different applications. And so this is sort of a vision of the things you'll need and how that might be connected and what the applications might be. So I think that gives us an idea. This is a visual that's a nice, ties it all together. So what are the approaches to quantum networking? So approach 1, we have 2 photons. So this is for entangling 2 separate nodes. And this was initially put out by Dwan and Kimball, as well as Christophe Simon and Irvine here in 2003, which has an entanglement swap in the middle. So the idea is that you have here, let's look at the Kimball proposal here. You have 2 atoms in a cavity, right? One cavity in cavity L, one atom in cavity R. They emit a photon. And the level system is such that you could have an H photon or a V photon emitted from this excited state. And you prepare your system in this 0 or 1 states. And the photon that's emitted is correlated with the ground state or the spin state of the atom that it's left in. And so you've got entanglement between the atom and the photons, polarization, so the energy level of, or the spin level of the atom, and the polarization of the photon. And then you send these to a polarizing beam splitter. So this is what we mean by our Bell state measurement. And then we make coincidence events here. And that, after this wave plate, that's an important part. But after that measurement, this Bell state measurement, you erase the which photon or which path information that each photon came from, and that projects the atomic systems into an entangled state. Right? And so each atom is now in one of these states. So this one could be in the 0, and that's the 1, or vice versa, 1 and 0. And so, great. Simone and Irvine, they proposed a similar idea. And then, one of the first experiments to be done with this was done with trapped ions by Chris Monroe, his group, in 2007, where he had a network, so two ion traps that are about 1 meter apart, emitting photons here in a similar way. We go through fibers, and we have our beam splitter, our polarization measurements, and we get clicks here. And a coincidence event will say, I've got these now 2 ions entangled, and you can measure that entanglement by reading it out. The rate at which entanglement is heralded here between these 2 ions goes as the probability to emit and collect a photon in trap A and trap B, so the product of those two, times the efficiencies of our detection. So that's an important point to scale. But another point to note is that the entanglement, the fidelity that you get of the entanglement here, so how good the entanglement is, doesn't depend on the probabilities here. So the problem, though, is that the rates are low because you need 2 photons, right? And with inefficient detectors, right, a small number times another small number is a really small number. It becomes a problem. So I didn't want to, go dwell on that. So the other approach, or another approach to quantum networking, is what's called the DLCZ protocol, or Dewan Serac Zoller Kimball approach. Dewan Lukin Serac Zoller. Here, 1 photon is involved. 1 photon's emitted from either this group of atoms L or this group of atoms R. And so we have a single photon potentially coming from here, or a single photon coming from here. It hits a beam splitter, and you detect 1 photon. When you detect 1 photon, you know that you've left one of these atoms in the excited state, the other's in the ground state. And that's entanglement that you can measure. So the rate of entanglement here goes as the probability for collecting photons from system A or system B times the efficiency of the detection here for both. Right, so we add the rates for those 2 possible outcomes, and that can be much higher. Right? So you should be able to get a lot higher rates. The entanglement fidelity, though, requires that these links between the atoms and this beam splitter is phase stable. And that's one of the key challenges for the DLCZ approach. Now, the entanglement fidelity also depends on the probability of collection efficiency, right? So, or the probability to generate photons. And that's a challenge here as well that has to be overcome. So I say it's high rates. So this is from October of last year from Delft Group, where they get a generation of entanglement across. So we have a 15-kilometer node, a 10-kilometer distance here between these 2 nodes. So Delft to some midpoint station, from The Hague to this other midpoint station where they're doing their Bell state measurements. So this is their midpoint Bell state measurement station. And what we can see is the rates of success. The rates are that's high. 0.48 hertz is actually not bad. Okay, but that's the state of the art for this protocol, as far as I'm aware. So to summarize, the current approaches, we have matter-based systems use entangled light to emitted by atoms, ions, or defect centers in solid-state systems to entangle 2 remote matter-based qubits. So so both of these approaches kind of fall into that. The disadvantage is that the rates are extremely slow. And the bandwidths are fundamentally limited by in these technologies by the line widths of the atomic systems. So that's a challenge. You can't go any faster. You could multiplex and have multiple memories or multiple of these atomic systems at a node, and that is something to explore. So one can also do what we call photon-based, where you have entangled pair sources. that are not deterministic. So at the moment, we don't have deterministic sources. So if you use these probabilistic nonlinear sources, there are extreme problems when you try to herald the entanglement. You still have what we call the double pair emission. So for the experts, there's still a limit to how well this can go, unless you have some kind of non-demolition measurement to say you've got photons, one photon here and one photon here, or you have some memory that you can load and know that you've loaded it. And that's the approach. It's a hybrid approach that this Center for Quantum Networks takes, is this entangled source and loading quantum memories that you know you've loaded them. So a heralded loading. And our approach in ASPEN-Net is going to take sort of a reverse of, it's going to meld the photon base sort of with the DLCZ approach. So we're going to use path encoding to generate entanglement. They're going to be heralded. And this allows us to use current source technology to build scalable all-photonic quantum networks. We think this is going to operate at much higher rates with heralded entanglement generation. And we believe we can carry out entanglement swapping operations and network protocols with a provable quantum advantage over other systems, because we think we can get much higher rates. And the approach will eventually integrate with the matter-based approach, we hope. So the ASPEN-Net approach, as we approach the hour, is based on what I would call Stephen Van Enk's single particle entanglement paper. Take a photon, put it on a beam splitter. And so send a photon, single excitation of the field onto a beam splitter, and what you generate is vacuum in mode A and one photon in mode B, plus one photon in mode A, vacuum in mode B, assuming a 50-50 beam splitter. Now, you can read Stephen's paper. I won't read it for you. This is a great little, it's 2 pages article in Phys Rev A. And the crux of the paper is that he argues that this could be used to load 2 quantum memories here and here, and produce the type of entanglement that you want to produce in the DLCZ approach. All right. So here we've got the emission of a photon and detection of a photon here. You don't know which atom cloud spit out the photons, and that entangles them in this ground excited state. Ground state excited state plus excited state ground state with this phase depending upon the relative phase of these 2 paths. So if we time reverse that, send a photon in, we generate that. So this is precisely the type of entanglement that Stephen discusses in this paper. Now, the idea of transduction from a photon source over here to match the modes, the line width, and the temporal mode shape that these atoms want, well, that's a hard problem that still needs to be solved. So our all-photonic approach to this DLCZ approach involves, now you can still utilize that entanglement that you've distributed across those 2 nodes. You could interfere that with 2 local oscillators, right, alpha and beta, and now measure some kind of entanglement here. But we can also do entanglement swapping in this protocol. So we could imagine we generate our pairs of entanglement here, we move through, and we get a click. Well, in that click on the left, we've generated a state between the left 2. So 1 is on the left, 0 is on the right here. So that's mode 1 is this side, and 2 is on this side on the right. And so 1, 0 plus e to the I delta phi, 0, 1, where these phases now depend on this path here. You get a click on the other side, you get a phase shift. So you go from the plus state to the minus state here with a minus sign in the middle. So the key difference for most other test beds is that we're using path encoding to generate entanglements that can be heralded. So these are our basic repeater architectures. It allows us to use current source technology, so single photon based sources, to build scalable all-photonic quantum networks. We can operate at high rates with the heralded entanglement generation because we can use high bandwidths of optical bandwidths. And there's a possibility to carry out entanglement swapping operations, network protocols that we will lead to a provable quantum advantage for different applications. In particular, we'll talk more in the series about those. And our approach can eventually integrate here with a matter-based approach, but we still have to solve the transduction problem. So the challenges, the opportunities for ASPEN-Net, I would say, are the phase-stabilized links. We have experts at NIST and CU who have been working on this to synchronize clocks across large optical fiber networks. We have high-efficiency sources and detection experts from NIST, CU, U of O, all optical quantum buffers, at University of Illinois in Urbana-Champaign. And one of the key things, as I say, we're going to have to figure out at some point the transduction problem, but we're kicking the can down the road, I would say, for now. So with that, thank you. Here are, again, our advertisement for the next series where Mike Mazurek will give us a deeper dive into our architecture for the path-entangled quantum networks. Followed that by, in early April, Paul Kwiat.
Sorry, I want to jump in, Brian,
Yeah.
just really quickly. Sorry. So these are actually the incorrect dates. The dates are on the website. So we had modified the slide. The next talk will actually be, because of the March meeting, we're going to shift things. So the next talk will actually be April 3rd, and that'll be Mike Mazurek talking about path entangled quantum networks. He'll go into more detail about what you just discussed.
I didn't get the memo, or I did, and I was just falling asleep. Sorry, thank you. Super. Okay, but please join us for those. And I also want to give a little shout out for the ASPEN-Net Town Hall that we are organizing in early June, so 2025, in conjunction with the Quantum 2.0 workshop that will be held at the Hilton San Francisco Union Square. And so there was a recent town hall last week by another NQVL center in New York. So we're the sister center, and we're looking forward to holding our town hall where we hope to bring in people from all areas of interest for quantum networks, particularly from the end user view. What we'd like to see is some good input into what direction we could be and should be heading. So with that, I'll take any further questions, or I thank you for your time.
Hey, thank you, Brian. Very, very good, very interesting talk. I did have a question, though, about the communication you're doing here was to establish entanglement between two quantum objects, I guess, right?
That's correct, yes.
Now, so what about if you had that and you wanted to move it to another physical location on some other spot, two other qubits?
Right.
Is that it's going to follow on with the discussions that we have coming up in the next sessions?
Let's just take this picture here. So suppose we now generated entanglement, I don't know, between this quantum system and this one over here. Right, so at the bottom right and the sort of bottom left. Now, if you wanted to shift that, right? So right now these are matter-based systems, and you would want to re-emit that or have somehow emit a photon back into the network and then route it back. So the approach that ASPEN-Net is currently pursuing is routing the entanglement to specific nodes. Once it's there, you could put it into your memory and do whatever you like with it. Right now, we are only focused on delivering the optical photonic entanglement to the different end nodes. And then I think your question is related to, well, okay, I've mapped it now into some stationary system, physical system, and now I want to move that somehow and take that entanglement and entangle something else. That problem, I think, is not yet. We're not addressing that problem in this project.
Yeah, I was kind of imagining you have some quantum computer that generates some result that involves entanglement. And you want to then move it to some other spot and do something else with it.
Yep.
That's a separate job then, huh?
Well, yeah, it's wrapped in what I call this transduction problem. So the quantum computers that IBM has, they are based on superconducting systems, and the types of electromagnetic fields, the photons that they interact with, are very very low energy, and so it's hard to send that out and then have that photon interact now with a trapped ion system.
Well, let's say you can solve the transduction. I mean, you still have the wave function of one quantum computer you want to move over into another one, I guess, and you can't duplicate it, you know.
Well, so what you do is you do what we call entanglement swapping, right? And so you're going to swap the entanglement. You have a photon that's emitted from your quantum computer, and if it's whatever wavelength it's at, it doesn't matter. And you're going to now have another photon that's emitted by your other quantum computer, and they'll meet in the middle. So let's see, think of this protocol here. So we have our photon here and our photon here, our atoms, our quantum computers. They emit photons, perhaps just one in the DLCZ approach, and they meet on a beam splitter, or the paths meet on a beam splitter. You get a click. That now entangles these two systems, right? And that's how you can link up two disparate or distant quantum systems. So the same thing would happen now in this scenario that you're talking about, where you have one system and you want to now connect that to something else. You would do what's called entanglement swapping.
Okay. All right, thanks.
Yeah.
I think just in the interest of time, we're past the top of the hour. We should probably ramp up. And in future tutorials, we've kind of designed things that some of the tutorials will be introductory, some will have a mix of introductory and intermediate material, and some will be introductory, intermediate, and advanced. So this was like our introductory tutorial, and next session, or next time in April, Mike Mazurk will be giving a talk that will maybe go into a little bit of a deeper dive into how some of these topics work. And it's of interest, we can certainly include things like teleportation in there as well, which would help with what James was talking about.
Yeah.
So with that, thank you, Brian, and thank you everybody for showing up for our inaugural meeting. And we'll hope to see you back here in April. And we'll be making the slides available, I think, as well as the recording of this talk. So thanks, everyone.
You.